Shufeng Hu, come from National Taiwan Normal University. I'm the chair of this fight, okay? And
好，就暂时这样。
now, please introduce yourself.
I'm Zhang Zihong from National Synchrotron Radiation Research Center.
I'm Liu Qianxiu. I'm from Taipei University of Arts.
So, hello everybody. Welcome to NTNU. I'm Cai Zisen from NTNU.
My name is Feng Xuan Zhuang. I'm from Sunya Center.
Hello, journalists and fellow students. We are MD Fresh from Mingdao High School. Thank you.
Opponent?
Hello everyone, we are Team XL5 from Concordia Middle School, and I'm the captain Zhong Youyan. He is Cai Bochen, he is Wang Boan, he is Chen Lifu, and she is Huang Yujia. Thank you.
You.
Hello everyone, we are Team Limited, and we are from Jingxing High School. I am Captain Cai Jingchen. This is Sun Jungjie, Zhang Ziwei, Xifei.
Okay, thank you. Okay, let's start the stage 1. Opponent, please challenge the question to the podium.
We would like to challenge problem number 9, light lister.
We will reject.
Oh, 现在开放12跟6这两题。
We would like to challenge problem number 5, synchronized candle.
We will accept the challenge.
Okay, we have 5 minutes for preparation. Please write down your presenter's name. put the text floor.
Good afternoon, juries and fellow contestants. We are at MD Fresh, and today we are talking about this topic, synchronized kingdoms. So first, let's take a look at the problem statement. Oscillatory planes can be observed when several kingdoms burn next to each other. Two such oscillators can couple with each other, and they will result in in-phase or interphase synchronization. And in the problem statement, we know that it's depending on the distance between the sets of the kingdoms. So we wanted to explain and investigate this phenomenon, which is in-phase or anti-phase. So here's our outline. So first, we'll show you the video and the phenomenon. And next is the oscillation of one kingdom to explain how one of the kingdoms will oscillate by itself. And the third one is experimental method. And the fourth is result and discussion. And next is explanation and conclusion. So in-phase synchronization means the plane of the two kingdoms will oscillate with each other in nearly the same period. That is, candle A and candle B's planes will move together. And anti-phase synchronization means the flame of the two kingdoms will oscillate with each other in an opposite period. That is to say, when candle A reaches the top of the flame, the candle B will start to oscillate from the bottom. So next, we'll talk about oscillation of one kingdom. So when we place one candle here and light up the candles, and even though it's just one candle, even though it's just one candle here, but it will still oscillate by itself because of the differences of oxygen demand and supply. Oxygen demand supply is very important to this kind of oscillation of one candle. So first, in this situation, the oxygen demand is smaller than supply, so it will gradually become bigger. The flame will gradually become bigger. It will become this, and then because of the bigger the flame is, so the oxygen demand will become gradually bigger. So then the oxygen demand will become bigger than the supply. So they will become smaller again. So this kind of oscillation will keep circling like this. So this is why one candle oscillates by itself. And here's our experiment method. So we need some candles made from wax, and a built-in smartphone camera, which is slow motion capture for 240 foot per second. And number three, we need an acrylic covering and a dome, which is one of our parameters. So in experiment one, we change the distance between the two candles, which is according to the problem statement. So we can move candle B left and right to change the distances, and we place a rule under the candles to measure the distances between the two candles. And the distance we measure is the middle of the flame, which is the burning part, and the candle B's burning part. So it will be all the same, and it's very accurate. And experiment two, we change the environment, which is open or closed environment. So this is the schematic illustration of our setup. So this is open environment. And next one, we put acrylic covering, acrylic dome on the top of the flame, and will cause this kind of environment we call it closed environment. So experiment one, we change the distance between the two candles, and we're ranging from 2.5 centimeters to 2.9 centimeters. The reason why we choose this kind of ranging result is because of this time of the flame will have in-phase changing into no phase. So we consider this is a really accurate distance for these candles to resulting in this kind of phenomenon. So in figure one, we showed you that distance between the two candles are 2.5 centimeters. As you can see, it is in-phase synchronization now. In figure two, we expand the distance between the two candles to 2.6 centimeters, and it's still in-phase synchronization at this time. As for 2.7 centimeters, it's now anti-phase synchronization. 2.8 is still anti-phase synchronization. And 2.9 centimeters, as you can see, we define this as no phase because candle A just not really oscillating very much, and candle B just oscillate by itself. So here's our results. Distance between two candles ranging from 2.5 centimeters to 2.9 centimeters. And the phases are gradually changing from in phase transforming to anti-phase, and to no phase. The reason why we call this kind of phase changing, we will talk about it in the end of our presentation. And the next one is experiment 2, which changes the environment, which is closed or open environment. So in figure 1, we showed you that distance between the two candles are 2.5 centimeters, and we compare closed environment data and open environment data here. So on the top, we can see it is closed environment, and it resulting in phase synchronization. As for open environment, it's in phase synchronization too. As for figure 2, distance between the two candles, we gradually expanding to 2.6 centimeters, and closed environment resulting in phase, and open environment resulting in phase synchronization too. 2.7 centimeters. Closed environment resulting in phase, but it's really not really obvious right now. As for open environment, in our previous presentation we have taught it is anti-phase synchronization. 2.8 centimeters, because closed environment is resulting in no phase, so we didn't put the result here. So open environment resulted in anti-phase still, and 2.9 centimeters, as we taught before, is no phase right now. So here's our result. Distance between two candles are the same, ranging from 2.5 centimeters and to 2.9 centimeters. So for open environment, it's still in phase transforming to no phase. So in phase transforming to anti-phase, and no phase. For a closed environment, it's from 2.5 centimeters to 2.7 centimeters are all in phase synchronization. As for 2.8 and 2.9 centimeters, they result in no phase. And the reason why we're talking about it now. Explanation for in phase, anti-phase, and no phase. So this is heat transfer. Radiation is a very thermal imager. So we use it to imagine the Gauss distribution. So as you can see, for in-phase case, the Gauss distribution is presented like this. So the red line represents the maximum radiation curve, and the black line represents the minimum radiation curve. So in this case, the maximum overlapping mark with red as 1, which is here, and the minimum overlapping the mark with black as 3, which is here, this small domain. So the overlapping domain in this kind of figure means the radiation will become bigger, and will become bigger at this time of the overlapping part. So when both of the candles reach the top of the flame, which is the red line, they will have a big domain which is overlapping. And when both of the candles reach the bottom of the height, which is the black line, they will still have a domain which is overlapping. So it will cause this kind of in-phase case. Next one is anti-phase synchronization. So in this figure, candle A's minimum is overlapping candle B's maximum, which is marked with S2, yellow one, and it is the red line. And candle A's maximum overlapping candle B's minimum, which is S2, which is green one. So at this time, so let's take red line for example. So red line, for example, it is S2, yellow one is overlapping. So at this time, the radiation will transfer from candle B and to candle A. So the candle A's flame will become bigger and will gradually move to the black line, which is this. So it's from this to this. So we'll call this kind of anti-phase case to occur. And the next one is our conclusion. So we talk about the oxygen demand and supply as regular oscillation. And the next one is the form of the heat transfer, which is what we assume that it is radiation. And that we talk about the overlapping radiation distribution comes from the the phase changes. Cause for the phase changes. Thank you.
The opponent questions reporter.
So the first question to the reporter. So first, how do you define in-phase and anti-phase?
In phase means the plane of the
Yeah, I mean, how do you define from the graph?
graph. It's we find the top of the period.
You also have to completely match together. So if there's a little bit.
Nearly.
So what's the range of that?
Range of the we have calculate some of.
Okay, we probably can talk about that later. So please turn to the page where you explain the oxygen supply. So by this you mean the oscillation of the flame just only caused by the oxygen supply. Then do you think you should consider other factors such as the thermal convection or radiation?
Radiation is on the last of our presentation.
So you mean radiation only causes synchronization, and the oscillation itself is only caused by the oxygen supply. Is that right? Okay. The next question, please turn to page 14. Page 14. Can you give a brief explain of why these two waves of the candles is different? You see, the one on the top is sharp. Why are these two waves different from each other?
This and this.
No, there's a red and a blue one.
Oh, sharper. Because
Time's up. Okay. Opponent for your preparation, 3 minutes.
One comment.
再举一下。现在怎么样？
你们直接接这一条。反正绳子够长。
那就这样切就好。
Okay, honorable juries and other competitors, this is the opponent from Opinion Selfie, and today I'm going to oppose problem statement number 5, synchronized candles. Here's the problem statement. Oscillatory flames can be observed when several candles burn next to each other. Two such oscillators can couple with each other, resulting in in-phase or anti-phase synchronization, depending on the distance between the sets of candles. Explain and investigate this phenomenon. I think our main focus will be the main cause for the flames to synchronize, and the boundary of two forms depends on the relevant parameters. And here's my structure of solving this problem. First, I have to analyze the main cause of the synchronization, which I think will be the single flame oscillation, like Coil mentioned, and the coupling between the two sets of candles. And later, we have to investigate the coupling between the relevant parameters, which I think includes 3 different types of heat transmission, which includes thermal radiation, convection, and the combustion of the flame itself. And then we have to investigate the boundary condition of the synchronization, which the parameter may be the distance between the candles and the paraffin consumption rate of the candle itself. And then here are the strong and weak points of the reporter. First, they have the very clear observation video of this phenomenon, but their definition of in-phase and anti-phase is not clear at all. And then they consider the situation of the open and closed environment, but they didn't consider the different oxygen consumption rate in the closed environment. And they have shown a clear experimental setup, but they didn't well explain this theory. They didn't mention the main cause of the synchronization, and they didn't quantify the theory of vibration of frequency or amplitude, and they have really lack of parameters such as gas constant or the external temperature might also be a parameter we can conduct in this problem. And then we can calculate, and then according to the theory, we cannot actually calculate and quantify the exact value of each, whether it's temperature, brightness, or the oxygen consumption of the candle itself. And then here's my point to be discussed. First of all, we have to discuss the flame motion, which includes in-phase, anti-phase, and the transmission phase, like the reporter mentioned, and the desynchronization. Desynchronization means the two flames are not coupled together. And then it will be the theory part. The theory was separated into 2 parts. The first is the oscillation, and the next one is the synchronization. The oscillation part, which I think includes the convection of the flame and the combustion of the flame. And the synchronization part, which I think it includes the thermal radiation, and the coupling will also be worth to investigate. And we talk about their experimental setup, which they have to maintain the air supply in case the environment that they are putting their setup in is lack of oxygen. And then we have to define each different phases. And the first we have to define the transmission phase of between in-phase and anti-phase, because that's the boundary. And then define the way to define that might be the phase shift or the period change. And then have to define 2 different synchronization, which is in-phase and anti-phase. And with the same way they can define it with the phase shift, period change, or the coupling strings among them. And then to the experiment, these brightness, temperature, and oxygen consumption might be a thing that in the experiment that they can testify. And then the frequency, amplitude, and boundary condition might also be affected by the relevant parameters. And the parameters that we can conduct can be the distance between the candles, the external temperature, and the paraffin consumption rate, and the median between the candles. Because first, the distance between the candles is going to affect the coupling strength of these two candles, and the external temperature is also going to affect the convection of the candle, and then the paraffin consumption rate is going to affect the combustion of the flame itself, and the median between the two sets of candles is also going to affect the radiation between the two sets of candles. And that's all for my report. Thank you.
Okay, discussion.
Okay. So back to the definition of the in-phase and anti-phase. And so how do you actually define the range of what is in-phase and what is anti-phase?
We calculate the period between this and this, and the gap between this, and use this to divide this.
Okay, so can you tell me what is the range that is set that equals to that represents the in-phase and what is represents the anti-phase? What range is that?
Okay, we divide this and divide this by this.
No, I mean, do you have the actual value of this phase shift between them?
Oh, we didn't show on presentation.
So what's the value of the range?
I haven't finished the calculation. We divide this by this, and then we use like a circle to define this kind of thing.
Okay, thank you. So turn to page 4, please. So you mentioned, so I want to ask is why is the brightness is different? Say you have the presenting the same environment and it's the same air supply, so why are these two things with different amplitude and different brightness?
Amplitude because candle have a string in the middle and we just burn that string. And in our experiment, we didn't consider this, and this is our fault.
So you also cannot control each control each candles, right?
Yeah.
Okay, so okay. So turn back to page 14, please. Okay, so what actually did you measure? What was the amplitude represents? Is it brightness, temperature, or other things?
The top of the flame.
Top of the flame. So the top of the flame cannot be well controlled. Okay, thank you. And then to your theory, which so get back to your theory. Do you think the air convection also will affect the convection of the air will also affect the experiment result?
We have considered air convection before, but if we consider air convection, then we can explain why anti-phase is possible.
Okay, so I think we have to consider all of it in order to give a theoretical model to fully explain this phenomenon. Thank you. In the next part, you have mentioned this part. You have mentioned the air radiation. So how actually did you calculate these radiation?
Oh, that is, we use this kind of equipment and just assume that's a shape.
Assume the shape. So what is the actual main cause for the two flames to synchronize?
Main cause is the coupling part.
So the coupling, so the the coupling strength is going to depend on the coupling area of this, right?
Just
Okay,
copy.
thank you. So, what do you think? I think might change. What do you think? What do you think the result might be when we change the velocity of the air convection?
Change the air convection.
Yeah, because we didn't talk about that part. I think that also affect the result very much. So can you give a brief explanation of your thoughts?
I think if the air convection velocity is bigger, but so the flame will be smaller, and I think the
So-
flame will be smaller.
Flame will be smaller, so how it's going to affect the result? Is the frequency going to be different, or the grip of the amplitude is going to be different?
I think from it because the distance between two candles, if you say that the velocity of the airflow is bigger, I think the distance will increase when it is in phase or in phase just all increase.
Why is that? Why is that?
Because
But you mentioned, switch to the next page, please. The page with the radiation. You only said the coupling strength will be affected by the radiation, but that's not really correspond to the convection that you just mentioned, right?
that is you asked me that if we increase the velocity of the airflow. So in our
That's airflow. Then this is radiation. So
yeah, so we just
the thing that you just mentioned is completely paradox.
in our experiment, we just consider the radiation. So there's no airflow consideration in our presentation.
So okay, so the back to the the problem of the air supply. And do you think the air supply is also going to affect the velocity of the convection?
Yes.
So you do actually consider the convection, but just a little bit. Okay, so in my opinion, when we increase the convection velocity, we increase the size of the flames, it is going to the airflow is going to rotate bigger, so we might decrease the frequency per load. Do you agree with that?
Yeah.
Okay, thank you. And then to the next question. So, what is the relation between the phenomenon and the distance?
What do you mean?
I mean, by changing the distance between the sets of candles over the phenomenon, how would the phenomenon change?
This
This and
changing the distance and.
oh, okay. So how do you define the transforming phase?
Oh, because we just show part of our data here. In fact, when we just analyze all part of 2.6 centimeter we find out that is in phase transferring to anti-phase. Just sometimes in initial part is in phase and then changing to anti-phase.
Okay. So did you measure the actual like the previous radiation graph that you showed? Did you measure each one of them to actually quantify the size of quantify the coupling strength? Did you do that?
What do you mean?
Did you in the previous graph you measure the radiation of two flames, right?
Yeah.
Yes, and did you measure all of these radiation under these different circumstances?
No, because the radiation, our figure of radiation, we just used to explain why cause in phase and anti-phase. So we didn't.
What causes interest in anti-phase? And this is actually in-phase and anti-phase change. So
Yeah.
the distance between the sets of candle it do actually affects the radiation effects from one of the candle to another, right? So I think you also need to give us that kind of graph. And then what do you think might change what if you what do you think that the result might change when you change the medium between the candle air or the gas that is burning. What would the result be like if you change the gas is burning?
We didn't consider this.
But you grasp, since you have give us a theoretical theory and your report does not have that much parameters to talk about, so I want to just discuss with you.
We may change the oxygen to our thing.
Yes. Yes.
Some of the gas won't really make the industry burn. So what kind of the gas you want us to change from oxygen?
Okay, time's up.
Thank you.
Moon, and summarize your discussion.
Okay, first of all we define the in-phase, end-phase, and transmission phase first, which we define it by the phase shift period, and when we talk about the theory, which is the convection and combustion will affect the oscillation of the single flame, and while we increase these things, the amplitude and the frequency might change, and while we increase the coupling strength and radiation, while we change the radiation between these two sets of candles, the coupling strength will increase, so that's why the phenomenon is going to change. And then to the experiment, they didn't measure the coupling strength while they changing these parameters. So I think it's important for them to actually consider the boundary range and the radiation coupling strength. And we can also do that. Thank you.
Okay, reviewer, ask questions.
My first question is for the reporter. I want to ask you, how do you track the lifetime of the plane?
Oh, yes. You mean how do we define the top of the plane?
Yes.
It's a tracker, and we use tracker to track the top of the plane, and it is heated part.
So what if when the plane stretches and so when the plane stretches, how do you
What the
define
mean
it?
stretches?
So like in facing it stretches and it separates. So how do you define the plane?
If it separates, we will track the top one.
And for both of you, so in reporter's experiment, you didn't see, you only see in-phase sync and no coupling for the condition with a closed environment. So what do you think is the parameter that affects that you cannot see the other two situation?
What situation do you think that we can see?
So when the recorder has a closed environment with the panels burning, you only see in-phase sync and no coupling. Can you explain why? You only see the two conditions with the candles coupling in-phase and no coupling. But there should be 4 conditions, right?
I think they just didn't conduct the experiment well, because if their theory is true,
I think that's enough. How about reporter?
Okay, so in closed environment, we find out, we know that, we assume that this will be wider, and this will be wider, this will be wider, and then these two of the radiation curve will couple with each other in
So my question is, why can't you see the other two situations? The antiphase and the critical point.
Antiphase and in-phase is in open environment.
So
And you
you're
are
saying-
asking closed environment.
So you're saying closed environment, you just can't see it anyway?
Just in-phase and no phase, no antiphase.
Time's up.
Thank you.
Okay, review the text report.
I'm the reviewer from Team Limited. I'm reviewing problem 5, synchronized candles. So first our outline, the overview, reporter's presentation, opponent's presentation, discussion, and then our Q&A. So the problem statement is just as the reporter had mentioned, so I will skip this. So summary of the presentation, their phenomenon, they demonstrated clear footage of in-phase and anti-phase synchronization, and also on the critical point, and I have also considered the condition with no synchronization. And their theory, they say the oscillation is caused by the oxygen demand and supply, and also the heat transfer from the radiation. And they did not consider airflow. And the experiment, they changed distance from 2.5 centimeters to 2.9 centimeters. And they changed the environment by open or closed. And their results is the phase changes between 2.5 to 2.9. And under two environments, there's different results. So for the reporter, their strength, they have sufficient data analysis, and they're constructed clear graphics. And for their weakness, they failed to explain the cause of oscillation and the lack of mathematical theory model, since there's only experiment data, and so they have also lack of relevant parameters, such as maybe they can stack a stack of candles, so that may cause the other two conditions under the closed environment to appear. And they have different time gap on the horizontal axis, which they show for their two graphs. So that would be affecting the understanding. So for the opponent, their strengths, they ask valid questions, and they mention coupling depending on parameters such as convection, which the reporter didn't consider that much. And their weakness is for the question time, they are trying to do something they should do on the discussion time. And their discussion, opponent asks, how do you define the range of in-phase and anti-phase? And the reporter says, they know how to calculate it, but it didn't finish the calculation. And second, the opponent asks, why are the amplitude of the two candles different at in-phase? And the reporter said, maybe it's because the middle part of the candle. And our opinion is, we think the candles may affect the phenomenon, but it is not that significant. And third, opponent asks, will convection and air conduction be considered in the experiment? And reporter says they did not consider it. And our opinion, we think the two parameters the opponent have mentioned should both be affecting the results, so they should be considered. And they asked, what is the main cause of the two candles to sync? And the reporter says, it is the coupling area. The opponent asked, if we increase the velocity of the airflow, what would happen? And the reporter said, they didn't use it as a parameter, so they cannot make a prediction. And in our opinion, we think they should consider more parameters. They asked, what is the relation between the radiation and the distance? And the reporter only showed the relation between the phenomenon
Time's up.
and...
Okay, reporter, make conclusion remark.
Okay, thanks for the opponent's great discussion and reviewers great. Okay, so here's our concluding remarks. So mayor question X. So the opponent asks, how do you control the amplitude of the flame? And our answer is the effect caused by the amplitude of the flame was too little to be considered. So we just ignore it. And the next question is, why didn't you include our air convection? And our answer is, it is not relevant since it doesn't affect that much. And the next, opponent asks, how do you define the differences between anti-phase and in-phase? And our answer is delta T divided by the larger T times 260 degrees. So effective discussion was being done, and we discussed the future parameters to do next. Suggestion for the opponent: try not to discuss irrelevant topics like air convection or other kind of irrelevant parameters when they don't affect the result, such as what kind of the gas is changing from the oxygen. Thank you.
Okay. Let's have questions from jury.
My question to if you have two candles, you put in some pistons, they are in phase. You say that I think you can see. Okay. Now, if you put a paper or plastic in between, or in left side or right side, what will happen for your observation? It's still in phase, become out of phase, or become cross. I think it starts from the total.
I think the result will be the same because in our experiment, we have seen it's just radiation, and radiation will affect by your
Opponent.
And if we put the paper in the middle,
or in the left side or right side. You say the two candles here, you see they are in phase. Then you put the paper between the two candles, or you put the paper outside. What will happen?
if we put the paper in the middle, it will soon cut off or weaken the radiation between of the transmission.
Still in phase or become out of phase?
It will become out of phase. And if we put it on the outside, I think it will not affect the result very much.
There are 2 points I think first of all, because I think air convection should be a very important part of the sink. So if we put a paper in between them, it will become out of phase. And second, because when it is in phase sinking, the distance should be very small. So if you put a paper between them, it should just burn out.
Any other questions from jury? No? Okay, let's prepare the score. Okay, you ready? Okay, for reporter. Seven, 5, 5, 6, 5, 6. For opponent. 7, 7, 8, 7, 7, 6. For reviewer. 8, 6, 9, 8, 6, 6. Okay, finish the stage 1. Thank you, everybody. We have break.
voice.
9.
We will reject the challenge.
Reject.
Coil was to challenge problem for mean speed.
We will accept the challenge.
Okay. Please write down your presenters. 15. Chapter 4.
Honorable juries and other competitors, I'm the reporter from Typt Excel 5, and I'm going to report problem number 4, wind speed. The problem says that an electric current flows through the coil. When the cold air flows over the coil's temperature will decrease. Investigate how the temperature drop depends on wind speed and what is the accuracy of this method of measuring wind speed. And we mainly focus on how to measure wind speed by temperature, the accuracy of the measurement, and also the parameters affecting the accuracy. First, we will show you an observation video, and in theory, we consider different kinds of heat transfer. Before experiment, we will show you an introduction about the experimental setup and also the equipment. And after that, we will define the accuracy and also do some experiment about it. The parameters are the wind speed and the power of loss supply. And the discussion is about accuracy, measurement, and also error range. Then we get a conclusion. And this is a simple record of the phenomenon. This is a thermometer which can detect the temperature of the coil and the wind at the same time. And this is a coil we already heated up by current. As you can see, the temperature dropped very fast in the beginning, but gradually slowed down and finally reached a balance because of power equilibrium. And here are some lag error of the thermometer, but that won't affect the result. We first change the initial temperature to see if it will affect the lowest temperature we want to observe. The initial temperature here means the temperature when we open the pump. And as you can see, no matter what temperature is starting to drop, they will meet the same lowest temperature at 48 degrees Celsius. It means that the initial temperature has nothing to do with the lowest temperature. So there is no need to control the initial temperature in the following experiment. In our theory, consider different kinds of heat transfer. The total power acting on the coil equals the power input of the current minus the power bring out by convection, radiation, and also conduction. And by estimation, we found that the part of the radiation and convection are extremely small, so we could ignore both of them. And according to thermal effect of the current, the power input of the current is always constant. But according to Newton cooling law, because the temperature difference between the temperature of the coil and the air becomes smaller and smaller, so the power of the wind will keep decreasing and finally reach a balance with the power input of the current. And we use the square of the current times the resistance to calculate the power input of the current because that it won't count in the heating effect of the current on the power supply. Although that will become take resistance, but we know how to calculate it. And according to the power law, we assume that the power of the wind is in proportion to the power of alpha to the wind speed and to the power of beta to the temperature difference between the temperature at the moment and the temperature of the air. And we assume the constant C to make an equation. And in power equilibrium, the power of the wind will equals the power of the current, also power input. And after simplify, it will become like this. And in the next 2 pages, I will say how to figure out the value of alpha, beta, and also constant C. And first, write down the equation we get in the next page, and then take a lograms of both sides of the equation, and draw a graph of the log wind speed with slope temperature difference. And it will become like this. The slope is minus beta over alpha, and the vertical intercept is this. And next, draw a new graph of the vertical intercept with the log power input. You will get a new slope which is the reciprocal of alpha, so we can get a value of alpha. And then substitute alpha into a vertical intercept in this graph, and also minus beta over alpha, we can find the value of C and beta. Here is our experimental setup. First, we will measure, before each experiment, we will measure the wind speed to make sure the wind speed is adjusted to what we want. And for measuring, we keep the distance between the air outlet and the thermometer is 3 centimeters. And after that, we will take away the thermometer and replace it with a coil. We first open the power supply to heat up the coil, and then open the pump. When the air is blowing, the thermometer can detect the temperature of the coil and the air at the same time. And here is the equipment we use. We use nichrome to be the coil because nichrome has higher resistance and smaller thermal expansion coefficient compared to the normal wire. And the pump can generate wind. The air valve can be used to change wind speed. And here is the experiment about wind speed. We tested 10 different wind speeds from 2 meters per second to 20 meters per second. And here is the temporal evolution of the temperature with different wind speed. As I mentioned earlier, the initial temperature is not very important, so we just need to look at the lowest temperature. And the red line, which represents wind speed, is 2 meters per second, set at a higher lowest temperature. and brown line which represent 10 meters per second stand at the lower lowest temperature. According to our assumption, the power of the wind is in proportion to the power of alpha to the wind speed. So it can prove that when the wind speed increases, the power of the wind will increase too, which makes the temperature drop lower. Here is the temperature difference varies with different wind speed. We may see a negative correlation. After take a logarithms, it will become like a straight line. And according to our assumption, the slope will be minus beta over alpha. And here I'm going to talk about how we define the accuracy. First, take a tangent slope of this graph. Choose the wind speed you want, and it will become like this. The temperature we measure will have a deviation because of the minimum scale of the thermometer, and the range is acceptable. After correspond the temperature to the wind speed you want, the wind speed will also have a deviation equals the temperature deviation divided by the absolute value of slope. And when power equilibrium, after calculation, the error range will equals the actual wind speed plus or minus this value. And if the derived value we got from the formula is within the range, it means it is accurate. And here's the experiment about power of current. We want to see how temperature drop will varies with different power. And you may see that this is the temperature difference varying with different power under wind speed is 4 meters per second. The power increase and the temperature difference will be bigger too. It is because that the current can provide heat, which makes the temperature hard to drop. So the temperature difference between the lowest temperature and the air temperature will be bigger too. And use our assumption to explain. The power of the current has a positive correlation to the temperature difference between the lowest temperature and the air temperature, which fit our experimental result very well. And here is the log plot of the wind speed and the temperature difference. You may see that no matter under which power, the lines are almost parallel to each other, which means that their slope minus beta over alpha are very similar. But still has a little difference, and I think the deviation is caused by radiation, which we already ignore because it is pretty small. And I'm going to talk about how to get the wind speed from our experimental data. First, draw a graph of the log wind speed with log temperature difference like this. And in order to get the slope, which is minus beta over alpha, and the vertical intercept, and then draw a Remark graph of the vertical intercept we just got with log power, you'll get a new slope, which is the reciprocal of alpha, so we can get the value of alpha. And then substitute alpha into vertical intercept in this graph, we can get C, and also put alpha into the minus beta over alpha, we can get beta. And here's the calculation result under 8 meters per second swing. And substitute the 3 into the formula, we can derive the wind speed from the power of the current and also the temperature difference between the lowest temperature and the air temperature. And the range between the two red lines is the error range. The blue dot means the derived value will come from the formula. If the dot is within the range, it means it is accurate. And when power input increases, the error range will become small. It is because that the higher power has a bigger absolute value of slope, so which will derive a small deviation of wind speed. And we also found that there is a measure limit of this measuring method. Take this power as an example. The horizontal axis is the actual value of wind speed, and the vertical axis is the derived value. We can find that when the wind speed is higher than 8 meters per second, there will be a very big deviation from the actual value and the derived value. It is because the temperature has fallen to a limit, so the temperature difference we substituted into the formula will be the same, and we will derive the same wind speed, which no longer increase but inaccurate. And also, power 14 watts has a limit of 16 meters per second because it is higher because that the higher power can provide more heat, which makes the temperature which means that it needs a more powerful wind to hit the temperature limit. And also, when the wind speed is smaller than 2 meters per second, the result will be mainly affected by free convection, so it will be inaccurate too. And as I mentioned earlier, the higher the power input is, the more accurate it will be. So, although the wind speed is too high, we can improve the accuracy by increasing the power. Take this 2 wind speed as an example. You may see that the deviation between the derived value and the error range becomes small when the power input increases. It means it will be more accurate. And we also found that the bigger the wind speed is, the more scattered the experimental data will be. It is because that the deviation of wind speed equals the deviation of temperature divided by absolute value of slope. So when the wind speed increases, the absolute value of slope will decrease, which will derive a bigger deviation of wind speed. And here comes the conclusion. We will assume a formula in order to get the wind speed, and which part I think is most critical is how to induct the formula because it is related to our accuracy. You may see that no matter on which power, the slope of the local part of the wind speed and temperature difference are almost similar, which is minus beta over alpha. And in order to get the value minus beta over alpha, we draw a graph of the log wind speed with log temperature difference. After get the value and also the vertical intercept in this graph, we'll draw another graph of the vertical intercept we just got with the log power input, and we will get the slope which is the reciprocal of alpha, so we can get the value of alpha. And then we can also get beta and C. And according to our experimental result, we found that the accuracy of the measurement will be affected by power input and also the wind speed. So even though the wind speed is too high, such as 20 meters per second, we can improve the accuracy by increasing the power. We can see the deviation between the derived value and the error range becomes smaller when power increases. And the measuring range and also error range of the measurement will be influenced by power input. When power input increases, the measuring limit will be higher, so we can measure more wind speed. But the error range will become small because of the bigger absolute value of slope. So the error range will become small, which makes it become more accurate. And this is my presentation. Thanks for listening.
Okay, opponent ask questions.
I would like to check for where did you do the experiment? This kind of problem.
We do it in the classroom.
And did you measure the temperature in your classroom and make sure that every time you do the experiment, you can control in the very same temperature?
We measure the wind speed, but the wind speed, only the wind speed won't affect the result because the result is mainly affected by the temperature difference between the coil and the wind. So it is the temperature difference, only the temperature of the wind.
So do you have some video that shows how your experiment conduct?
I took it in my setup, and we will heat up the coil first, and when the temperature meets the temperature we want, we will open the pump, and the current is still generated, and the air will blow in, and the temperature will drop.
And I would like to know that did you check the resistance of your experiment, that you can make sure every time you did it and when you heat up the coil, is it correct? And
We measure it, and we found that the resistance varies with temperature is very, very small. We used a simulation to calculate the resistance and found that it only will increase a little when temperature increases.
so you did a simulation and experimental comparison of your resistance?
Because
Then
in fact,
opponent, your preparation for swimming. Okay, opponent, please take the floor.
Hello everyone, I'm Team Limited and I'm going to uphold problem. We're going to uphold wind speed. And this is the problem statement that it says that the focus point is the cold air and the temperature drop and the relationship of wind speed. So we're going to discuss about this kind of parameters, and we need to check for some accuracy for this experiment. And this is the overview of the reporters. And the phenomenon, they showed some pictures for their experiment, and they have some simulation to do with their some measurements. In the theory, they use power law and talk about the current, radiation, wind, and conduction. And the results, they measuring the range and power, and their accuracy and power area range. They also do a good measurement and some calculation. And for the experiment, the initial temperature, they say that initial temperature doesn't affect this experiment. And also they do some comparison of the power of the wind and the temperature. And another comparison is the current react to temperature. And for the reporters, their pros are clear derived some formula that related to their experimental results. And second, clear experiment setup, and they showed a good picture for their experimental setup. And the third one is sufficient calculation and data analysis. So with this calculation, we can know that how some parameters will be related to this experiment. And some accounts of reporter is, we suggest that you can show some video to demonstrate how you conduct the experiment, and we can know about how the environment and some structure of your experiment. So I would like to discuss with the reporter. So first I would like to discuss with you that the experiment environment will affect your experiment. Like when you have a wind source blow out of your environment, will it affect your experiment? Like some you did a very open place. Yes. Will this affect your experiment?
No, because the temperature we calculate it with the temperature difference between the temperature of the coil and the temperature of the air. So when we already minus the temperature. We minus the temperature of the wind, so the temperature of the wind won't affect the result.
Another one I want to discuss is you change the power of the current, right?
Yes.
And so, what is your some power source? Like you control the.
We use the DC power supply.
And you control all the current the same in every experiment.
Yes, current is the same.
Just change the power of your supply.
Yes.
Okay. And so
I answered wrong. The current won't be the same. It will increase and the power will increase.
Okay. So you say that radiation is not your point to discuss, right?
Yes.
How do you think that radiation will probably affect in this experience?
You mean the radiation of the whole coil or only the wire?
The whole coil.
I think the bigger the radius is, the surface area will be more, so it will be more inaccurate because the power of the wind brought by the wind will be more. So it will drop, the temperature will drop fast, which causes that the wind speed we can measure becomes.
So if you discuss the radiation, it will affect your accuracy of the experiment.
I think it is one of the advantages.
And have you ever think of changing your coil for another variables?
We tested very many coil, but this coil is we think the best one.
You choose the biggest resistance.
We have tested many coils, and this is the best one.
So what did you have? What have you measured from coils? Like what did you choose this for?
Because this coil, the material is the nichrome, and nichrome will has a higher resistance, so it can make the main heat the main current effect will happen on the.
You have some bigger resistance, like the temperature raise or drop will be more obvious. Right?
Yes.
And how did you do? How many circles did you do with your?
We doesn't control the circle. We control the radius of the whole coil.
But
so if it is longer, it will be more circle.
Do you think that the more you have around it, and will it affect the area that exposed to the environment?
It will affect only a little, so we can ignore it. I think.
So another question is, do you think that if we do this experiment in a nearly closed environment, how will this problem affect?
I think it won't affect anything because, as I mentioned earlier, we calculated with the temperature difference, so the environment won't affect much.
How can you check that? Because your temperature drop to the same degree, right?
It won't drop the same degree at each time of the experiment. It depends on how high the wind temperature is. If the wind temperature is higher, the coil's temperature will be higher too.
Okay.
But the temperature difference between the two is constant.
When you have a wind source that blow over the coil, the resistance will change, become, right?
Only change a little.
Okay, so you didn't measure it, or?
You mean when the temperature becomes higher, the resistance will be
higher, or yes?
As I mentioned in the simulation, this vertical line is the temperature, and it is not very clear. Sorry. It is the temperature, and this is the resistance change depends on the wind speed. You may see that the temperature drop nearly 100 degrees, but the resistance only decreased very little.
So this is a simulation you have to.
Yes.
Okay. And you have a graph that you show the temperature has been high to 360 degrees.
What do you want to ask?
A graph that shows to, yes, can you talk about how you do experiment? Yes.
we first turn on the power supply, and when the temperature meet the temperature we want, which is 200 degrees Celsius, and it meets these 5 different degrees. And when the coil meets this temperature, we open the pump. So the initial temperature can be different.
So, as you did many times of your experiment,
Yes,
did you check that the accuracy is the same?
it will all, the lowest temperature will all stay at 48 degrees Celsius. It is very accurate.
For all the experiment you did?
Yes, we did many times. We did it almost 10 times for each experiment.
So, with your whole experiment, what did you get the most significant accuracy for doing this experiment?
It doesn't have a most significant accuracy. What do you mean?
You have another question is, what is your accuracy of your anemometer?
We don't know how it's accurate, but it is a machine, so we can only think that it is accurate.
Okay, so
And we use the thermometer we use to measure wind speed. Although it has an error, but I think it is very small. I believe that.
So I think that for reporters experiment we have to.
So you want to make a conclusion?
So for the reporters experiment, they have a good accuracy on their experiment, and they control the every time the when they change the DC power supply, they can know that some relationship of the experiment. And another point is they can check the temperature or some related parameters to be controlled in the whole experiment. And I think that experimental environment will affect the whole experiment, because it is an open place that will have some convection or
Time's
some.
up. If you ask a question to both of them.
Honorable judges and fellow students, this is the reviewer from Team MD Fresh. So first of all, I would like to make some clarifications. So the first one is, you guys mentioned that you didn't consider room temperature, right?
We consider it, but
It will not affect a lot, so you ignored it, right?
because we calculated with the temperature difference, so only the temperature of the wind won't affect.
But I believe that, in my opinion, so let's say this room is 0 degrees, and you are doing the experiment, right? If that is the condition, then the coil will cool down very, very fast. So that will definitely affect your results. So that is the point that I think you guys missed out. Okay, So for the second one, can you go back to a lag arrow that you mentioned? The lag arrow. Yeah. No, below. Yeah, the lag arrow. Do you consider other factors, or do you think it is only because of the thermometer?
It is only because of the thermometer.
Okay, so do you consider radiation or conduction being in place in this experiment?
We listen to the student.
Oh, okay, it's okay. I'll ask him first. Do you believe that radiation and conduction will act in their experiment?
I believe that conduction will do more significant influence in this experiment.
Yeah. For me as well, I also believe that radiation and conduction should be included as well, although they will not be affected. They will not affect a lot, but they should still be considered. Yes?
We already estimated, and for power of radiation, you can see that the formula is like this. And
Yeah.
we assume the coil is a black body, so we can calculate the maximum of the
Okay,
radiation.
I'll have to cut you off because I'm running out of time. So basically, you are just saying that you will ignore it because due to your calculation, it is not very effective.
And yes, it is
Okay,
only one.
thank you. For a final question, I would like to ask, how did you measure the temperature of the coil?
We use
You use
a
a line to directly connect to the coil throughout the entire experiment, right?
Here is a sensor.
Yeah. So you connect it directly to the coil for the entire experiment, right?
Yes.
But however, do you notice that the pump will be also pumping
We have checked-
onto the sensor as well?
We have checked that the sensor is very small.
Yeah, but it is connected onto the coil. So when you're blowing the wind, the thermometer will also get impacted by the wind as well. So the thermometer will also cool down itself, which means that the temperature you get will not be very accurate.
But the
What do you
sensor
think
is
about
very
it?
small.
Huh?
Okay, time's up.
But it is still on the coil, so it will still be impacted by the wind. Yes.
Okay, preparation for the reviewer. Okay, reviewer, please take the floor.
Okay, so honorable judges and fellow students, this is the reviewer from Team MD Fresh. Okay, so this reviewer would like to review problem 4, wind speed. So I will not restate the problem statement again. And so some overview of the reporter, some advantages, which are a lot. First, many mathematical functions were explained, and they have also explained a very detailed theory as well. And they also demonstrate the phenomenon clearly. They explain the way of conducting the experiment very well. and many parameters were considered as well. And I also explained the relationship between different parameters with correct labels on the graph. They explained the applied law clearly. The error bar is being provided as well. The conducted reliable simulation was very good as well. Some suggestions will be that, first, they can explain the reason behind the chosen parameters. Second, they can explain the further relationship of the calculation. And third, although the equations are thoroughly explained, but the explanation might be too quick, and which would cause some confusion of the audience. So the overview of the opponent, some advantage is that they explain their own point of view to the experiment. Second, they catch most of the critical problems of the experiment. However, they should try to hold on to those critical questions once they catch it. Just don't let go with those critical questions. Yes. And so the first discussion was, the opponent asked, where did you do the experiment? Did you make sure the environment temperature? And the reporter said, we did it in a classroom. There are more important parameters to be considered other than room temperature. But as mentioned by this reviewer believes that room temperature should definitely be considered. For discussion 2, the opponent said that, did you check the resistance of the experiment? The reporter answered, the resistance is too little enough to be ignored. And the reviewer opinion is that this reviewer agrees with the reporter since the resistance in this experiment is being calculated and is little enough to be considered. For discussion 3, the opponent asked, what is the power source and are currents in different experiments remain constant? And the reporter answered, the current will increase and the power will increase too. The reviewer agrees with the opponent because the change in power source might affect the relevant parameters. For discussion 4, the opponent asks, how many cycles of a coil did you tie, and what will this affect the result? And the reporter answered, we control the radius of the coil. The effect is little enough to be ignored. My opinion is that I agree with the reporter because the radius of the circles have a direct connection and will not affect much. So the reporter did a very good job. So I will just jump into the conclusion. So overall, good discussion. Major questions were being discussed, so everyone did a very well job. However, there are some points that both teams missed out throughout the entire competition. The first point is that they didn't discuss radiation and conduction because those two, although those two will not affect a lot, they still actually affect the results. So they didn't discuss this. And also, they didn't consider room temperature as well, which will definitely affect the result. And finally, the way they measure the temperature is inaccurate due to what I just explained. They directly connect the sensor onto the coil, which will still be blown by the wind. So it is also inaccurate. So these are the 3 points that we think both teams missed out. Thank you.
The reporter concluding remark.
Here my concluding remark. First, we assume a formula in order to derive the wind speed and find out the accuracy. And when we deducted the formula, we found that the slope, which is minus beta over alpha, nearly the same under every power. And we also found that here is a process when how we deduct the formula. First, we use the slope and the vertical intercept to find out the constant such as alpha, beta, and c. And according to our experimental result, we found the accuracy will be influenced by power input and also wind speed. When the wind speed increase, it will become more inaccurate. But when power increase, it will become more accurate. And measuring range and error range will be influenced by the power input. When the power input increase, we can measure more wind speed. And when power input increase, the error range will become small, which means that it will become more accurate. And here's for the setup, we use DC power supply to control the current, and also we conduct every experiment in the same room, so the environment won't affect our results. And also we use the nichrome because it has a higher resistance and also its thermal expansion coefficient is very small, so it won't deform after reheating the coil. And also in our experimental result, it is very accurate. In the discussion, the opponent asked me some parameters, but that won't affect our result.
Okay, time's up. Question from jury.
So, the review, the reporter, you have done a very excellent measurement, because you have done a lot. But in your discussion, you have ignored some parameters. For example, the radiation, the conduction, and also the change of the electric resistance. So I want to ask, can you estimate what is the percentage of the radiation you ignored to your results?
Because we only estimated at the maximum of the power of radiation. We assume that the coil is a black body, so the surface emissivity we substitute into it is 1. And after calculation, it is only 1 to 100 compared to the power of the current. So we think it is small enough to be able.
Just 1%. 1%. Yeah.
Okay, I want to ask a question. You change your background, I mean a different room temperature for it. Or what's the range of the temperature for the heat or the mentioned? The temperature of the background. So in the 20 degree or
The range of the room temperature.
highest and lowest.
It is, we control it in 25 degrees.
So you always
the
put
average
heat
is
in 25 degree.
the average is only 2 degrees.
So you control your background or your room temperature always in the same temperature.
Yeah.
Have you tried, for example, in some the turn of air conditioning to maybe 15 degrees? Do you still get the same result? Have you tried this?
We have tried it. It won't affect the result because we only.
What's the lowest temperature you have?
The coil lowest temperature will change, but the temperature difference won't change.
Temperature difference will change.
Yes.
Any other questions?
Can I have the second question?
Okay, yes, please.
So, for the reviewer, you have also done quite good work. And I want to ask, it's just curious. You have asked the reporter have ignored the conduction, thermal conduction.
Yes.
So do you have any idea if I do not want to ignore it, then how can I measure it? I also have no solutions.
I think you should like measure the temperature around the coil as well, like at the same time. So we can know the air conduction around the coil, and to make sure that the heat is actually conducting the same temperature all around the coil. So basically just attach a thermometer around like the coil, so to detect the temperature around the coil.
I agree with the reviewer.
So for the
I think you also need to measure the temperature differences to do something related to radiation.
thank you.
Thank you.
Okay. Let's go. the reporter. Seven 987 for opponent. 65565 for reviewer. 879876. Okay, thank you everybody. We finished this.
We would like to challenge problem 6, irreversible accreditation diagram.
Number 6.
We would like to challenge problem 9.
Problem 9.
Line whiskers.
The problem of number 40 is available.
14?
Yeah.
I would like to challenge problem 14, dynamic hydrophobicity.
Okay, please write down the presenter's name on the blackboard. reporter takes the floor.
So this is the problem. When the drop of liquid impacts on horizontally moving surface, the droplet may be reflected or not, depending on the speed of the surface. Investigate the interaction between a moving surface and a liquid drop. So we're going to focus on the point that about the droplet reflected and the speed of the surface. This is the observation. So we will separate two conditions. One is while the liquid drop contacts with the moving surface, and the droplet may be reflected in a small angle and be driven away fast. And another condition is when the moving surface is not fast enough, the droplet will be directly driven away or stuck on the surface. And the theory is about hydrophobic is when a droplet contacting a hydrophobic surface, it will maintain a large contact angle, and so it can form a perfect drop shape, so that it can definitely reflect it over the surface. And a very important theory is the H-bond in a droplet. So H-bond can help the droplet maintain a perfect drop shape and minimize contact surface and maximizing the contact angle. So it can make the phenomenon of reflection obvious. And we can discuss with two theories. One is Winslow state. So droplet directly contact with the microscopic structural rough surface homogeneously, and this is the this picture. And another case is Cassie vector state, and it is about the surface is not homogeneous, and we call it heterogeneous. So as I talked about before, the larger contact angle forms can maintain the droplet shape, so it can make it reflected. So where our hypothesis is the contact angle and the horizontal speed. So the phenomenon is mostly depending on the horizontal speed and droplet size. And other condition we need to consider is the material of the surface and the liquid's physical property and vertical distance. So we are not able to observe the 100% reflection situation. So the closest situation is to, as I said before, maximize the reflections number and maximize the reflection. The closest situation is to minimize reflection number and maximize the reflection type. So this is our variation. We're going to discuss on horizontal speed and droplet size and physical property and some materials of the moving surface. So this is experiment 1. We use a continuous tracks to maintain a moving surface. And as we can see, we use some materials like the socks and moving continuously, so the droplet from the rotate drop down. But the problem is to check the vibrating droplet, and it is difficult to check the speed because of the materials. So we changed another experiment. We used a power supply and to apply to the motor and make a moving surface, and we call it this. So in this experiment, we choose to change the speed of the moving surface and the vertical distance and the material of the moving surface. And the first one is I want to define the drop. This one is we use blue tape to control the size of the droplet, and we have measured that the average volume is 0.008 mole. And about the rotating surface, and we have investigated different speed by changing radius and voltage. So as you can see, the material of the moving surface is we use different kind of sandpaper, and the number of sandpaper is 100 and 120, 150, and 180. So as we can see, we control the vertical distance and the speed of the power supply, and the droplet size and the property of liquid. And so we can get the height of the reflecting droplet and the number of droplet scattered. And so another experiment is we differ the vertical distance from the plate, so the droplet will drop down in different velocity. And this is how we control it, and we also get the number of droplets scattering and the height of reflecting droplet. Okay, so as we have collecting many data, we can show that the material of horizontal moving surface can be very important. And as we can see, the more rough the moving surface is, the more obvious the phenomenon can show. And this is how the different number of sandpaper shows that the highest point that droplet reflected out to a long line, and we choose the highest point and the lowest point to make this chart. And so as I said, the droplet is more likely to scatter on rough surface, and the minimum of reflection height didn't change significantly, just in this changing material of the horizontal moving surface. And the maximum of reflection height increased as the surface becomes rougher. So as we can see that the moving surface material can help the droplet reflected more obvious, and when you have a smoother moving surface, the droplet will stuck on it and will not reflect it at all. Okay, so and we change the speed of the power supply, and in a faster condition, the droplet is more likely to scatter, and can also promote the height of reflection. And a positive correlation between speed and reflection height is more obvious. So it is easier to think that when the faster the disk moving, the time that the droplet contact with the moving surface is lower, so it is obvious that the droplet will reflect. Okay, so and the other experiment is the vertical distance, and we show that how much difference compared to the 20 centimeter data show how much difference compared to another ones, and the number of reflecting droplet will decline when the vertical distance was changed. And the droplet volume, the measurement of reflecting height decreased intensely when the volume decrease, and percentage of droplet scattering increase obviously. Okay, so this is the analysis. Height of reflecting droplet. The measurement of reflection height increase when the surface becomes rougher and when the speed increases. And it is easier to check and show when the droplet is smaller. And the minimum of reflection height didn't change significantly. And the number of droplet reflection, more likely to scatter on the rough surfaces and when the speed increase and when the speed increase, the more obvious the phenomenon will show. So this is the conclusion. The best situation for this kind of this experiment is we can control the smaller droplets and rough surface to make it reflect and higher horizontal speed so that the contact time will be lower and the long vertical distance then the droplet drop down. Thank you.
Okay, question from the opponent.
Hi, fellow delegates and the honorable judges. I would like to ask, is air resistance considered in your experiment?
We can consider the because we choose to
Just yes or no?
no.
Okay. Can you control the speed of the rotating plate?
Yes.
Okay. Can you control the contact angle of the droplet?
Yes.
Okay. Is the horizontal speed considered as a kind of force?
Yes.
So it's okay. It's a force, right? Can you tell the reason of a high speed scatter? Do you think it's going to scatter more?
The scatter means that the one droplet scattered from many numbers of small liquid.
Okay. Can you define other modes of the droplet when it contacts with the surface, like fall rebound, corona splash, or inclining this deposition?
No, we didn't define that.
Okay. Where is your camera set? Because where's the camera?
Aside from the rotating moving surface.
Okay. Do you have a demonstration phenomenon video?
No video.
Okay, just a picture of the
Yes.
setup. Okay. So how are you able to measure the contact of the droplet with the surface without a video?
We choose to put we open a light to brighten.
Okay. So what is the FPS of your camera?
60 FPS.
Okay, time's up. Opponent preparation for 3 minutes.
Fresh, and I'm going to talk about problem 2, dynamic hydrophobicity. And the problem statement, and I won't go through it, but the key points that we think is the speed dependent of the plane and the parameters upon the drop, like the vertical force of it. And summary of the reporter, their theory was hydrophobic, and the larger contact angle will form a better drop shape. And H-bound is to minimize the contacting surface. Maximize contact angle results in not, the experiment setup is they use a continuous track and track the moving surface, but it failed, and then they used a rotating disc, and in success. The volume of the drop will be 0.008, and they use sandpaper as their surface. And the perimeter will be the material of the surface and the vertical distance. So for reporter, advantages are they have a good diagram, and it's short, accurate, clear, and precise. Its suggestions are like maybe consider more parameters because there's actually 2 forces, and there's like velocity and a lot of things that you can change. And its lack of theory, the only theory, the hydrophobe, is rather vague, and its lack of setup diagram and the demonstration video, and their definition of the droplet of the motion after the contact is very unclear, and there lack of the formula to actually know the relationship between the contact and the form of the motion. And they should explain more about the mechanism behind the motion. And they can quantify the graph because the graph is not able to show much relationship from the 2 dependent variable and the independent variable. And more data sets can be provided for a better accuracy, and they can show the error bar of it because from as far as I see, there's no uncertainties in their graph. And they should provide information like the velocity of the sensor and maybe describe how high the accuracy is high. So points to be discussed is definition of the rebound, splash, corona splash, and other kinds of form of the after contact. And the setup of the experiment, how the whole experiment is done exactly because the foot page per second is only 60 FPS, and the discussion of their data and possible parameters that they could add. Yes.
You can discuss.
So as you say, the foot page per second is 60, and 240. But I think that is not enough to see the reaction because from our experience in our experiment, our high-speed camera have a FPS of 871, and as far as I know, that is only enough to see the phenomenon.
We also to check the number of scattering points if you use the slow motion to film it, so we can show.
Okay. Is Weber number considered in your experiment because there's 2 forces, and the reason why the droplet can reflect is based on the surface tension and the cohesive energy of the drop. So is Weber number considered? Weber number is the ratio of surface tension and inertial force. And if a Weber number is smaller, then the importance of surface tension is higher. So there can be 2 Weber number in your experiment. So the 2 Weber number should be. When it goes down, it creates a velocity in, and your rotating plate creates a force as Vp. So you can have 2 Weber numbers, Wen and Wet. So if you can calculate it through like applying this into your like a XA like dimensionless factor, then you can find out the relationship between these 2 forces.
I think we can only consider how to check the
can you show me the experiments there? No, the second one. So so that's a DC voltage supplier, right? And that's a that's a disk.
Yes.
So if you can control the DC voltage, the amount of voltage being supplied into the disk, you can control the speed of the disk.
Yes.
But you just told me that you cannot control the speed of
We can control that. Oh, no, we can control it. I think that. We can control that.
Can you explain that? What is the force like? Do you go to the graph of the page 44? The 20 the previous page. So there's three vertical distance and there's number of droplets. Can you tell me the relationship between the vertical distance?
We chose we define the vertical distances for to change the height of the droplet, and we assume that how many numbers of the droplet reflected.
So if it is able to reflect, are there any forces that it gains? Because it has when it reflects, it needs to goes up, right?
Yes.
The drop has so there must be a force to like make it go up. Can you tell me the relationship of the force and the vertical distance?
I think we are not focusing on the force that this graph is not focusing on what the force is.
Yeah, but the vertical distance is a force. It's gravitational force.
Yes.
So
it will affect the normal force.
Yeah.
That the droplet goes up.
Okay, so can you tell me what kind of force is making your droplet to reflect?
It will have a normal force and friction. So the droplet won't go definitely up.
Yeah.
It will go like.
So you're saying that there's a rotational force.
Yes.
So it don't actually reflect like straight up. It reflects like so if it is like in a 90-degree situation, the normal force acts like this and your friction force acts like this way. So is it possible to make it reflect upright? Right to the right.
Yes, yes.
So if it's being reflected, then there's going to be air resistance. And so it is not considered. Okay, so I think if air resistance is being considered, can make your the like how you control the droplet of reflection like better and precise. Like you can know the boundary region of how the height and the horizontal force and the air resistance. You can know like which number can make a higher reflect.
Okay, so I think that point we will interview.
Okay. So can you go to experiment the experiment setup? Where is the camera?
From this side.
Is it on the same level as your plate?
We film it. We just focusing on the light we pointed because we want to make sure the droplet can immediately drop down in the same place.
Okay. So okay, you can drop on the same place.
Yes, we control it.
So the camera should be here, right? Somewhere around here. Because the angle of it can affect your result of seeing the drop.
We just film it and this work and we control the droplet down this pole.
Okay.
So it doesn't focus on the way we film.
Okay, and why is the dropper being staying constant on this radius? Because as you know, different radius have different velocities. So why is it here?
It's just picture like.
Yeah, but you say your dropper is in a constant place every experiment.
Yes, but another experiment is we differ the height that the droplet drop.
Okay. So the only parameter is the height.
We change the height
And the material of the surface.
and yes, and the moving velocity of moving surface.
Okay. Okay. So what velocity will, like, there's air friction when you're spinning the plate. When the plate is spinning, you can feel the air, like there's wind. So there's going to be air friction, and the spinning if you say your droplet is rotating, right? When it goes down, does it rotate, right? As you said? Yeah.
We consider the air flow, but it is hard to measure the air flow, so we just ignore.
So you ignore the, okay. We believe that calculating that can make, like, because there's going to be a difference of how the speed of it, because the air under the drop, there's going to be an airfield under, yeah. So there's going to be different velocity of wind on the bottom of the droplet and on the top of the droplet, right? So maybe consider that can let you make sure the rotational, the angular momentum of the drop. Okay, so do you consider surface tension and surface energy in your experiment?
We just control the surface, the different surface.
The different surface. Yeah. So
the material.
So you didn't calculate the surface tension when it is touching the. So basically, the reason, do you know the reason why it splashes? Like why it splash?
So we assume that it's the
So the reason of the splash is because that when it is content, when it's content, the normal force breaks the cohesive force of the water drop, and then the surface energy is going to increase. So because the contact area is increasing and the surface tension decreases, right? So and then the surface energy is going to then decrease because it has to go up. So then because when it goes up, the contact area decreases, right? Because surface energy equals to the product of surface tension times contacted area. So when contacted area decreases, the surface tension increases, and which brought back to that leading the force of the cohesive force to brought back the drop to let it reflect.
Time's up.
So the summary of our discussion, that we talked about surface tension and the possible parameters and the air resistance. So there are quite a lot of parameters that are not controlled and not discussed in the experiment conducted by the reporter. So this, if they consider this in their future experiment, it will make their experiment more precise, and like it will have extra like data, and they can see more relationship because they didn't consider like Weber number, surface energy, cohesive energy in their experiment. So, and they say that the force of reflect is being given from the normal force, which the normal force will then destroy the form of the shape, because the structure is not strong enough and the cohesive energy is not enough.
Okay, time's up. Reviewer, ask questions.
For the reporter and the opponent, I want to ask that how the air resistance will affect the reflection height. It will become higher or lower.
I think it will become, the airflow is hard to measure, so we assume that it will be lower.
And
We will say that it will let the reflected height become lower because the.
Okay. And next, for the reporter, why the speed increase, the reflection height will increase too?
Can you repeat it?
As you mentioned in the report, I think you mentioned it. Why when the speed increase, the reflection height will increase too? Can you explain with a physical explanation?
We think that the faster it is and the contact time will increase, so we can definitely drop close up.
And for the opponent?
For the speed, do you mean the vertical speed or horizontal speed?
Vertical speed.
Vertical speed. So I believe that there's a boundary region that if the speed is over the boundary region, then it will become scattered or deposition because there's too much energy inside. And if it is inside the boundary region, then it will reflect.
Okay, thank you. And then for the reporter, what is your definition of reflection number in your presentation?
We film it and just check the how many shape of the perfection of the scattering like this.
And then for the reporter, what do you think the boundary limit of this reflection phenomenon? Boundary of the velocity.
We didn't do the experiment yet. We check the boundary.
And for the opponent, what do you think the boundary limit of velocity in this phenomenon?
The vertical velocity.
Yes.
What do I think about the boundary of it?
Next. And for the reporter, did you think that when the droplet is dropping, it will cause a deformation? Do you agree?
Yes.
And then how did you control the contact angle because it will move?
We didn't get accurate the contact angle, but we just make the
We believe that there's going to be deformation if it's too high.
Okay, thank you.
Okay, time's up. 2 minutes for review of operations.
competitors. I'm a reviewer from Team S601, and I'm going to review the dynamic hydrophobicity. And here's the problem statement. When a droplet impacts on a horizontal moving surface, it will reflect or not, depends on the speed and investigate phenomena. And we think we should mainly focus on why will this phenomenon happen and how the speed of the surface will determine the result. And the reporter did well on the clear setup picture, but he didn't have the observation video, which I think is very, he should have an observation video. And he didn't have the quantitative explanation, only discuss the phenomena. And he didn't compare the experimental data and has a physics explanation. And for the opponent, he asks about a definition about a phenomenon, which is reflected, not reflected or splash. And he point out the error caused by setup. And he mentioned about air drag, which will cause the height to become lower. But he didn't talk about his own setup. He didn't able to give a theory to explain the phenomenon to it. And they first discuss about the air resistance. And I think when the mass is smaller, the releasing height is higher, and the air resistance should be considered like this formula. And for Weber number, I think because the surface tension will increase as the Weber number change, so it is important to give the Weber number in the experiment. And as I mentioned, the surface tension is very important. They discuss about it also. And I think the surface tension is important in the contact place because it will affect the force distribution about the normal phase, which will cause a different deformation. And here's the point is, the reporter didn't consider the air resistance will affect the result about the height and the droplet motion after the first reflection. I think if the velocity didn't decrease very much, it will reflect second time. And he didn't define the contact angle, which is he didn't define the contact angle clearly. And then about the splash or reflective, he didn't define very well, and he didn't give clear boundary conditions of about velocity or so on. And he didn't analyze the whole force acting on the droplet, and I think it's very important because maybe because it is a whole system. And he didn't say how the material will affect the result clearly. And I think the reporter should consider the acceleration, motion, and also the opponent.
Okay, time's up.
Thanks.
Reporter make concluding remark.
I think the ratio of surface tension and measure force we need to consider in the future, and some of the experiment parameters we need to control also. And air resistance and friction we need to bring into our theory for calculating some reasons that will affect the number. And the reflection is caused by normal force breaking with cohesive force. At this point, we will check for how the reflection will be like, and the whole motion, the reason that caused this phenomenon. So in the future, we will check the accuracy and control the skill with films and some parameters like the speed of disk and some physics parameters that we need to check, and we need to bring a complete theory to model the experiment.
Okay. Any questions from jury?
I asked a few questions. From the beginning, the reporter doing the experiment from the linear velocity, then change to a circular motion.
Yes.
Okay. Do you see there's any difference in the distribution?
Just because the track, we can control the track.
If you can control, then you the number of things.
From their report, they say that the first setup has their surface, like their moving surface is not like stable, so they think that, and if in velocity, I don't think it will change, but the velocity of the rotating plate will be certainly faster because the radius of the plate will affect the velocity of it.
I think if it is a linear motion, if the velocity is constant, but if it is a circle, it will cause acceleration. So it will become a different circumstance.
Any other question? No? Okay, let's next go. Okay, for the reporter. Five, 4, 6, 5, 6. For opponent. 7, 7, 7, 8, 7, 6. For reviewer. 7, 7, 6, 9, 7, 7. Okay. Let's give yourself a big hand.